Hi, this is my introduction for the lab called Coupled Oscillators for our course Physics 300 Lab. That's the physical sciences for teachers here at CSUDH Hills. When I introduce this lab, I like to review one thing from a previous lab and then give you actually a little extra material that goes along with the lecture, which is not the phenomenon we'll be exploring in the lab itself, but that'll all fit in within about 15 minutes. I said I want to start with something from another lab, something that you've all done before. It was the Simple Pendulum Lab. And in the Simple Pendulum Lab, you took a system like this, and maybe before you even got the physics, this was a good lab to explore how to measure things. You were given a formula to check, and this formula, one of the things I always tell people is what's important is not only what's there and how it's there, but what's not there. The formula says that at capital T, the period, because period begins with T, right, is equal to 2 pi, that's just some number, times the square root of L over little g. Now, little g, the acceleration due to gravity at the Earth's surface, is also just a number. It's not going to change for doing this lab. L is the length from the pivot point to the pendulum, and as I said, part of what's important is how that's there. So when I take this pendulum, if I make it shorter, the period, how quickly it goes back and forth, changes, and it gets noticeably quicker. What's not there is also important. That is, there's no m in that formula. The mass does not appear. So if I take this pendulum and do this, and you did it with actual stopwatches and timing, if I throw another washer on there, so I got twice as much mass, it still takes just as long to go back and forth. The period did not change. Also, to a very good approximation, if I go to a bigger swing, the period did not change. There was no variable there, nothing that referred to how big a swing you're doing. Okay? So that's just something I want to remind you of from your previous experience, because that is related to what we'll be studying actually in this coupled oscillator lab. But before I get there, I have one little other piece that I want to get to that'll relate to your lecture more than the lab. There we go. I have here a string with a few washes on it. I like to play with this, it's kind of fun. When I have the simplest system, it's just a pendulum, again, the time it takes to go back and forth, the period, or along with that the frequency, does not depend to any great extent on how high I swing it, does not depend on the mass. But this is a very simple system. If we had 2 washers, I've got another simple natural pattern that can repeat itself without really pushing. We call this kind of pattern a normal mode of the system. So there's one way like that where they swing together. But there's another way I can do it, and I like to go around just because it's easier to keep track of it, especially when I'm talking. This is a noticeably quicker pattern, something with a much shorter period, higher frequency. It is another normal mode of the system. So I claim that these are the only 2 such patterns that will sustain themselves, the only normal modes for this simple system. If I get 3 washers, you might guess, you'd be right, but there's essentially 3 normal modes. And one of them, you can probably guess, it's when all of them swing together. The other 2 might not be so easy to guess exactly what they look like, but the quickest one is like that. It's kind of interesting because the bottom one barely moves in this normal mode. And the intermediate one, which is the hardest to keep track of for me, just physically, is kind of like this. Oop. There, I got it. If I go a little too fast or a little too slow when I started, it doesn't quite work right. This subject of normal modes you will run into in lecture, actually more when you talk about waves than just oscillations, but it's all related to this coupled oscillator issue. Now, the system you're going to look at in this lab, and it's related to things in the lecture as well, is this here. I have a string tied to the ceiling in this case. You can't see where it's tied up, I don't think. And I've got 2 pendulums hung from that string. Now, I just want to make a couple notes about doing the experiment if you do it yourself. The effect that we're going to study will work if the masses are different, but it's easiest to see what's going on if the masses are the same. Okay. The other thing is, again, it will work otherwise, but it works best if you space these out in a way that makes the section between them horizontal. Okay. So what we're going to do is we're going to look at the coupled system, the pair of oscillators, and pendulums in this case, and we're going to see what happens to one when I do something to the other one. Now, I've got it set up at first with one much longer than the other, and the whole point of the lab, the whole thing you're asked to study, is changing the length of one of them and see what happens to the other one. Now, for the single pendulum, I'm just going to hold this one so it's not doing anything. For the single pendulum, this is exactly the system I had before. You might have trouble being sure exactly where to measure the length from, because there's a piece of string sideways and a piece of string that's vertical. I'm not worried about that, because you're going to have 2 of them and they're both going to be hung the same way. Now, for this single pendulum, the normal mode is determined by the string's length, and the natural frequency, that's a technical phrase there, natural frequency for it, is determined by the string's length. The phenomenon we're going to look at is called resonance. And the idea of a resonance phenomenon can be a lot of different things in a lot of different systems specifically, but generically, the whole idea is if you get good timing, if you push the system with the right frequency, that is one of the natural frequencies, you can get more and more energy into the system. So, this is, on my right hand, the pendulum I'm going to be watching to see what it does. And the one on the left, right now, is a much longer pendulum. So, when I excite the system, when I give energy to it, when I swing this longer pendulum, it is affecting the string above, the coupling in this coupled oscillator, but it is doing that at its natural frequency, which is not going to be the same as the natural frequency for the one at my right hand. So you might say, what's this got to do with resonance? That's the point. You will not see a resonance, I claim, and in fact, let's do the experiment. I swing this, excuse me, and what you see is this one on the right does start to move a little. The system's bouncing a little. I try not to bounce it too much, but it's hard to do it perfectly, and we're not that worried for this level doing it perfectly. But this never really gets going. This thing's been swinging for some time. It's still got most of its energy, and this one's just bobbing around a little bit. I could tie this up to make it shorter, but I like to do this little trick with a pen. The pen is very, very light. This way I can make things shorter and longer and shorter and longer as much as I want. So I'm going to wind a lot of that string up here on this pen. And I claim that the pen makes virtually no difference because it's so light. And I further claim that you will see that because you'll notice the system doesn't have the string go 2 different ways where the pen is. Now I'm trying to make it so that, oops, a little more, so that this is noticeably shorter than the other one. You might say, quite reasonably, why didn't I just start with the other one? I'm trying to make a point about the effect on a certain part of the system by changing other parts of the system. Now I got this pretty short, not super short, but noticeably shorter than the other one. My claim is something similar to what happened before, but you will notice a difference in the behavior. Something vaguely similar will happen. So I take the shortened pendulum and I swing it. Again, there's bouncing. This is starting to move more. In fact, maybe I didn't shorten this enough. Hold on. This time I'm going to tie a little piece. Make it even shorter so you can see the effect better. Now, I watch as this starts, and this one does start moving more than it did before. Bouncing a little bit, but not all that much. But now it seems to be having erratic behavior. It started moving, and then it gets a little jerky, and now it stopped again. This is still going on. Now this is, again, moving a little bit, but being jerky. Again, no real big transfer of energy from this side to this side. So now, and I'm going a little quickly here, I want to get to the point where I expect to see this phenomenon of resonance. It's a fun word to say, resonance. I want to make the natural frequency of the one at my left hand match the natural frequency of the one at my right hand, so that I am driving the system, pushing it, with the frequency it needs to go higher and higher. Now this is just like pushing a swing in the park, right? When you have a kid, you push a swing, you don't push as quickly as you can if you want it to go high. You don't push whenever you feel like it, slowly if you want it to go high. The right way to get it to go high is to push with the right timing. And people know this intuitively, but you don't think of it as a physics phenomenon necessarily. You don't have to push hard. You just have to push with the right timing. Now, when I push with my hand, it's boom, boom, boom. When I drive with this, it's going to be a smooth motion that's driving that. And I've got them nearly, but not quite the same length. Let me pull this up just a hair more. I want to make it nicely matched and, oops, make that nice and horizontal. This height, take one more turn on there. And the height of these, pretty much the same. Okay. So now they're matched, and I claim I'm going to see this phenomenon of resonance. So this one on my right, I'm making still. This one on my left, I'm going to swing, try not to bounce it much. And when it starts, you can see right away that although the motion of the left one is not so effective, the right one is starting to swing smoothly. In fact, the amplitude, how high the swing is getting larger and larger. There's more energy being put into this, and the energy has to come from somewhere, so it comes out of the one over here. And now this one is stopped, and that one is going. So we should see the same phenomenon going the other way. The energy should transfer back. And that's what we're starting to see now. This one is starting to move, the one on my left, as the one on my right has less and less motion. So in a single pendulum, one of the things you may have talked about, when you talked about it in class, was that the energy goes from potential energy to kinetic energy to potential energy to kinetic energy to potential. The type of energy changes back and forth. In this slightly more complex system, for each pendulum that's true, but the total amount of energy on one of these gets transferred to another one. And then when we wait a little time, that second one, the one by my right hand, has very little energy, and it's being transferred back to the first one, the one on my left. That's what's going on here. Energy is moving from one part of the system to another part, from the other part back to the first. And it works this way smoothly because resonance requires that the two parts of the system, the two oscillators which are coupled, have the same natural frequency. A word about doing the lab. When you do this, if you make that string across very, very tight, and if you think about the limit of that, if you use the bar there, then one of them can't really get the other one moving. So you won't have a very good transfer of energy if you've got the string too tight. If it's too loose, and it hangs very far down, it will work, but it might be hard to see what's going on because the things will swing so much up at the top. So again, it works fine if the masses are different, but it's more obvious and you see it better if the masses are the same. And you want the string pretty loose, the string that goes across the horizontal one, pretty loose, and you can push around the knots here so that the center section is horizontal. That will make the effect most visible. To do this lab, you'll be asked to maybe fill out a sheet or write a report. We'll want pictures of your setup, and we have questions within the lab about resonance phenomena, and some of us put in questions about how energy moves through the system. So specific directions on what to write, what to submit from your lab instructor. I'm just trying to introduce the whole thing. Thank you. Enjoy.